We're now going to talk about the concept of downwash. And downwash comes usually from the main wing. So if we have the main wing here and we've got a horizontal tail sitting behind it, we understand that the main wing is altering the flow and creating this sheet of vorticity that gets shed. And so the flow in the wake here is actually at a lower angle of attack than what the main wing would be seeing. And to predict the effects of downwash on this horizontal tail is actually rather complicated. And the only way to predict it accurately is actually to use CFD or experimentation or high fidelity simulations. And actually, the numerical lifting line algorithm does a fairly good job of also predicting this downwash. And other vortex lattice method or panel codes, those types of things can also capture this, because this is mostly an inviscid phenomenon. But today we're going to learn a way to approximate it in the absence of those simulations. And so we're going to come up with a simplified model here. Let me zoom in just a little bit. Okay, so and I believe this model was first published by McCormick, and others have shown similar things. We're going to follow the development in Warren Phillips's Mechanics of Flight book in his second edition. And so basically, we're going to replace the vortex system here by a single horseshoe vortex that lies there along this wing. And it has some strength and is creating downwash that looks something like this. Now notice that I didn't actually draw it all the way to the wingspan. We'll talk about that in just a minute. But we're going to put an x-axis in here. Y will be up, and then Z will actually be out the left wing. This is our traditional aerodynamic coordinate system that we've been using. Okay, and we're going to, the wingspan itself is B. Let's put that up here. So that's the actual wingspan is B. And we're going to have a different span in here that we call B prime. B prime is the distance to that vortex, and which actually doesn't go all the way to the wing. The reason it doesn't go all the way to the wing to the wing tip is because we're placing that vortex in what you can think of as like the center of vorticity. As you move downstream from the main wing, the vorticity, remember we have an entire sheet of vorticity being shed here from the trailing edge. But as you move downstream, that sheet kind of rolls up into two main vortices. And the center of that final vortex system is inboard of the wingtip just a little bit. And it depends on the wing planform and the lift distribution on there. But basically, you can think of this as like a center of vorticity that's being shed from the wing. Usually our wingtip vortices are much stronger. So the strength of these vortices, if you look at this sheet, is really strong out here near the wingtip. And so the center of vorticity is very close to the wingtip. Okay, so let's talk about, so the downwash is, we're going to call this V sub y. That's the velocity in the y direction at any location back here in this system. So we're concerned with the velocity in and out of the page here, and that velocity is proportional. The induced velocity there is proportional to the strength of this vortex system gamma. So we've got a gamma here that tells us the strength of that horseshoe vortex, and that strength is related through, you're familiar with the Kutta-Joukowski law, that lift is equal to rho v infinity gamma. And so that gamma actually is proportional to the lift on the main wing divided by rho v infinity through some proportionality constant. And we can non-dimensionalize that, and if we then divide by 1/2 rho v squared SW, then we see that this is also proportional to v infinity times the lift coefficient on the wing. So the velocity We're just walking through a chain of things here to show that this velocity, this downwash velocity, is related to the lift coefficient on the main wing. In fact, it's directly proportional to that, as well as v infinity. And you get there by thinking through this process. Now, that these proportionality constants depend on several things, and so we're going to approximate what those would be. But the main concept here is that Vy is directly proportional to V infinity times the lift coefficient. Okay, so our downwash, epsilon d, if we use a small angular approximation, the downwash is equal to Vy over V infinity. And actually that should be negative Vy over V infinity. And so if we divide over V infinity here, over to this Vy, then we see that this is now going to be proportional. We're going to have some proportionality constant multiplied by the lift coefficient of the main wing. Okay, so what is that proportionality constant? Well, Phillips shows that you can write this equation. So epsilon d as a function of x bar, y bar, and z bar, and let's define those really quickly. So x bar we're going to use in our new coordinate system is equal to x divided by the span of the wing over 2, okay? And y bar is equal to y over the span of the wing over 2, and z bar is equal to z over the span of the wing over 2. So this is kind of a non-dimensional coordinate system that we use here, x bar, y bar, and z bar. And within that, you can work out the math of what this of the induced velocity at any location here in this system if your horseshoe vortex looks something like this, and it comes out to look like this. So rather than write this down, I thought I'd just copy it here. But you can see that this is dependent on x bar. We've got x bars and y bars and z bars. It also depends on kappa b, which we'll talk about here in a second, as well as a kappa v factor. So we're going to have two kappa factors here. Depends on the aspect ratio. And let's see, anything else to point out in this equation? I don't think so. So anyway, this is what the equation would be for the downwash using the small angle approximation here. And you could plug in your x, y, z location at any location in this system and get the downwash angle. Okay, so we see that this depends on these two factors, kappa v and kappa b. So kappa v is the vortex factor, and kappa b is a span factor. Okay, and we can actually get both of these from the analytic or the infinite series solution to lift inline theory, and so I've written those down here as well. Remember when we express the lift distribution on the main wing as a function of these Fourier coefficients, then anyway, kappa v and kappa b can be computed from those. Okay, and kappa b actually has a kappa v in the denominator here, which isn't obvious from Phillips's book, but you can see that if you just plug this in right there. That's what he actually has in his book. So kappa v and kappa b can be computed from these, and Phillips actually has some figures where he's pre-computed this as a function of aspect ratio and taper ratio. And so you can use in his book, these are figures 4.5.2 and fig 4.5.3. So those two figures you can pull out information, or if you don't have a straight tapered wing, then you can compute your own using a code for lift inline theory. So anyway, you can get it either way, but that's how we get kappa v and kappa b, and then we would plug that into this equation here. So we're actually going to simplify this just a little bit further. One thing to note is that the downwash distribution along the horizontal tail depends on location, right? So we can see that our downwash is a function of x, y, and z locations. So even the distribution along the horizontal tail will change, right? From the center line out to the tip, you'll have a change in that downwash. But as a first approximation, since the gradient in here is usually rather small, very close to the center line of this wing, and so we can actually approximate this by assuming that we're going to assume that the downwash is constant across the entire tail and compute that from the value here at the center. So in that case, we can plug in z, or z bar equals 0, into this equation, and that simplifies this quite a bit. In fact, we can then write, so I'm just going to say, if we assume that z equals 0, okay, we're just going to use an approximation by plugging in z equals 0, then we can write this downwash is equal to a kappa v times a kappa p over kappa b times the lift coefficient of the main wing divided by the aspect ratio of the main wing, where kappa p we get by simply plugging in z bar equals 0 into this equation over here, and a bunch of stuff falls out here, and we're able to get this kappa v here in the numerator. You see that? We're going to end up with a kappa b in the denominator. And then the remainder of the stuff depends on this x bar and y bar. And I'm actually going to write it a little bit differently. I'm going to actually define an x hat, which is simply x bar over kappa b, and a y hat, which is y bar over kappa b. And then you can write this kappa p equation as 2 over pi squared times y hat squared plus 1 multiplied by 1 plus x hat times x hat squared plus 2 y hat squared plus 1 divided by x hat squared plus y hat squared times the square root of x hat squared plus y hat squared plus 1. Okay, so we got that by simply plugging in z bar equals 0 over here and simplifying this into now yet another factor that's going to be called our position factor, kappa sub p, and now that can be plugged into this original equation here for the downwash. And so these three are constants once the geometry of the wing and the location of the horizontal are set. And we see that this is just an estimate again for this proportionality constant for how the downwash is related to the lift coefficient of the main wing. Okay, so that's our simplified model. Now there's one other thing that we can add. I believe it was McCormick that first suggested that you could also add another approximation here to capture sweep. So if you think about sweep for just a second, the effects of sweep. So we could build a vortex system that includes the sweep along the chord of the main wing. All right, so if this is our main wing, we can place our vortex system along that. Now, sweep actually ends up affecting this in multiple ways, though. So sweep has an effect on kappa b because it changes the lift distribution along the wing. Remember, kappa b is a ratio. Actually has to do with how far this center of vorticity is relative to the wingtip. Okay, and so it would change that because the lift distribution on the wing changes once you add sweep, and kappa v also gets altered because your lift distribution is different, and so anyway, it affects both kappa b and kappa v. But at a very first approximation, again, we can assume or make this estimate that kappa B and kappa V are independent of sweep, which really isn't true, but this is, again, just a first approximation. So we're going to keep these approximations for kappa V and kappa B and simply add a new sweep correction factor that gets multiplied by this kappa P, because now your horizontal tail back here is affected by the proximity of the fact that these have been swept back, and so the position of this horizontal tail or kappa P here is going to change. Okay, so we've got an estimate for that. We're going to just add in a new kappa factor here and say that epsilon D is equal to our original kappa V, our original kappa P, our original kappa B, and we're now going to multiply this by a new kappa S, and then everything else is the same, lift coefficient over aspect ratio of the wing. Okay, and kappa S, this is again straight out of Phillips's book, but he says the approximation for that is equal to, I'm just going to write it down here really quickly. So x bar minus s bar over t bar. He adds some new variables in here. X bar, which we'll define here in just a second, r bar plus t bar times t naught bar squared minus x bar squared divided by r bar t bar times r bar t bar plus r bar squared minus x bar s bar, and all of that divided by 1 plus, got a x bar times r bar squared plus t naught bar squared minus x bar squared divided by r bar squared t naught squared. Okay, and he defines an r bar is simply equal to the square root of x bar squared plus y bar squared, and an s bar is equal to kappa b times the tangent of your sweep angle lambda, and t bar is equal to the square root of x bar minus s bar squared plus y bar squared plus kappa b squared, and t naught bar is equal to the square root of x bar squared plus y bar squared plus kappa b squared. Okay, so again, you can use these equations to estimate what kappa s is. He actually also has a figure in the book. This is figure 4.5.6, where he's pre-computed this for some example cases. So you could just, if your scenario matches the information in that figure, then you could just look up a value off of that figure. So this is, again, just a rough approximation for the downwash on a horizontal tail that's sitting behind a main wing. And again, really what we need to do is get this from full CFD or experimental data, or at least a panel code or something like that that can capture this at a little bit more fidelity. But in the initial phases of design, this actually, you don't want to neglect downwash in the initial phases of design. And so this can give you a rough approximation for what that downwash would be earlier on in the design. Now, because we've added so many approximations, let's look at just a couple more that would even simplify this further. So these are really rough approximations, but the horizontal tail, sits behind the main wing, and in the limit, as the tail moves further aft or goes to infinity, the influence from the bound vorticity up here diminishes to 0. And so all that's left is the influence of these two trailing vortices. And so in the limit, as x goes to infinity, then we can actually simplify this a little bit more. So kappa p is going to approach 4 over pi squared. And let's see, kappa s goes to 1 because the sweep doesn't matter anymore. And so if you do that, then epsilon d now can be approximated as 4 times kappa v over pi squared kappa b times the lift coefficient on the main wing divided by the aspect ratio of the main wing. Okay, so that's even an easier approximation. All you have to do is calculate kappa v and kappa b and assume that x is far enough downstream and that sweep doesn't matter. Okay, so we can even take this one step further and say, what if we just assume that we have an elliptic lift distribution? And in that case, then kappa v equals 1 and kappa b equals pi fourths. And so we can plug this in as well to that and even get a more rough approximation. The epsilon d is equal to 16 over pi cubed times CLW over the aspect ratio. Okay, so this is now an extremely rough approximation. If you're still in the early stages of design, where maybe you don't even know what the planned form of the main wing is going to look like, or you're still iterating on some of these really rudimentary parts of the aircraft, then you can at least use something this rough as an approximation for the downwash, and obviously it has a lot of approximations built into it. But that's better than nothing. So again, we do not want to neglect downwash in the early stages of design. And here we've presented a few different ways to approximate that downwash early on, which then would need to be refined in the later stages of design with higher fidelity simulations or experimentation. So one final thing about downwash. So this is our general form of this downwash equation. And remember, this is the downwash on an aft tail caused by the main wing. And we'd like to write that as some epsilon d naught plus epsilon d alpha times alpha. And you can see that this is just a linear function of angle of attack. All of these terms in here are constant, except for the lift coefficient on the main wing, which is a linear function of angle of attack. So we can write it this way, where epsilon d naught is equal to kappa v, kappa p, kappa s over kappa b times the aspect ratio of the wing times the lift coefficient on the wing evaluated when alpha equals 0. Okay, so even at 0 degrees angle of attack, there may be some finite lift coefficient on the wing. So that would be epsilon d naught here. And then epsilon d alpha, or the downwash gradient, would be kappa v, kappa p, kappa s over kappa b times the aspect ratio of the wing in the denominator there, and then times the change in the lift coefficient of the main wing with respect to alpha. That's an alpha there. Or we can write that as, let me make that a little smaller. We can also write that as CL wing alpha, or the lift slope of the main wing. Okay, so this is probably the way that we'll apply it mostly in this class. We'll divide this up into an epsilon d naught and epsilon d alpha. Now notice that this constant out front of both of these is the same. So we have some constant out front of epsilon d naught and epsilon d alpha, and then we're just epsilon d alpha just is multiplied by the lift slope of the main wing, and epsilon d naught is multiplied or has the lift coefficient of the wing when the angle of attack is 0.